So here we go. It is Monday, the 22nd of February. We're almost done with February, folks. And right now, we're also nearing in on the end of our evolution unit. We spent the first week talking about Darwin and natural selection, survival of the fittest, and those concepts. We spent the second week going over a project where you enacted natural selection on your chosen organism, getting random events for what occurs in the environment, and then you needing to imagine what adaptations could your species evolve that would help them to overcome that changing environment. This week, we're going to take a look at the end of Darwinian natural selection, which is what we're going to cover today. We're going to finish shoring up all of the pillars that Darwin used to support his theory, all those posts that held it up and have survived hundreds of years of scrutiny. And then we're going to start talking about modern evolution, because our understanding of how life works is much better than Darwin's ever was. And so with that increased understanding, we've been able to move in and better clarify some of the ideas that he had, some of the concepts that he did not understand. So that is our goal. Now, in order to reach that goal, let me show you where we are. We're in Schoology, as always, unit number 5. Here is our PowerPoint, same one we've had in the last several weeks. Once again, just posted here for your ease of access. Today, we're going to talk about the Evidence of Evolution Lab after we do our notes. That will be a separate video. And of course, the turn-in. So this is going to be our Monday, Tuesday work. So let's get into exactly what it's about. What are those last things that Darwin used? We know he used the fossil record, because in his time, we were starting to dig up a lot of dinosaur fossils and other fossilized organisms and starting to question, where does this fit in? We know that he used the geographic distribution of species, how we see things that are clearly related on multiple different continents. And in the fossil record, how we see the same fossil found in places that are literally the world away from each other. But there were a few more things that he really focused on also. And remember, all of this was done by taking a look at those adaptations, those inherited traits that offspring get from their parents that make them more fit for their environment. Well, one of the things that Darwin noticed was that in samples of organisms collected from all over the world, there was this amazing similarity in their bone structure, their skeletal structure, especially among the mammals, which you can see here: human, cat, horse, bat, and dolphin. And if you take a look, we see the same exact bone pattern showing up again and again and again. The only difference is little tweaks to the length. Sometimes, like in the horse, you can see that the two bones fuse together into one bone. But all mammals share the same idea of one bone in the upper arm, two bones in the lower arm, lots of little bones in the wrist, and then your hand. And this was termed homologous structures. Now, anybody who's been watching my videos, anybody who's been in my class, by now, if you see this prefix, homo, you should immediately know what it means. The rest of the word is not important, because homo is Latin for the same. So if you see homologous structures or homo something structures, all right, we are looking at the same structure. Dead giveaway, makes it super easy. It's interesting to note, though, we don't just see it in skeletal fossils like this. We've also started to look at embryos developing offspring. And we find this craziness. So we've got a fish, a salamander, a tortoise, a chicken, and a human. And if you take a look at stage 1 of the early embryo, wow, there's a lot of similarities going here. We all have gill slits. We all have a tail. Everything has this weird curled tadpole type of shape. This is intentional. This shows that we are closely related. Now let's take a look at the mid-stage embryo. All right, the fish and the salamander, these two have both separated, but they're still very, very similar to each other. A little bit less so to us. So we know that these two are closer related to each other than they are to humans. But among the tortoise, the chicken, and the human, once again, you would be hard-pressed to really tell the difference between these 3 embryos if you were to just see it without it being color-coded. And, of course, then we get down to the mature. I don't know the artist, how they did this arm. It's the weirdest, swoopiest arm I've ever seen, but, whatever. The similarities, the same developmental structures that we see here fall under this homologous structures. Yet more evidence to support that we came from the same original ancestor. And that pattern of development is shared by all organisms with a backbone. All right, we also have analogous structures. So this is the opposite of homologous structures. This is proof that throughout evolution, different unrelated species have evolved the same adaptation, but not the same way. So, case in point, the fin of a shark, the flipper of a bird, the flipper of a dolphin are all evolved to aid in swimming. But if you'll notice, skeletal structure and stuff is not at all the same. They are not related to each other closely, and so they all arrived to the same point, but they got there on different paths. Also, over on the right-hand side for flying, a bird, an insect, and a bat, all 3 of them fly. But if you take a look at their wing structure, wildly different from each other. So these are analogous structures. Same function, they have the same job, but they come from an unrelated source. And finally, I think the coolest one, vestigial structures. Vestigial is an old term for leftovers. All right, and vestigial structures are going to be parts that used to be used. They used to provide something. Now they do not, but they have not completely disappeared. They still exist as a part of the organism. So this is a whale. And if you were to take a whale and you were to slice it open and dissect, there go the lights, slice it open and dissect it, you would still find these vestigial remains of their pelvis and their femur right where you would expect to find the hips along their spinal cord. They did have legs once, and while they have disappeared, for the most part, there's still this little bit of leftover, still this evidence that they once walked. Why else would a whale have these freely floating bones sitting right in the hip level? And don't get me wrong, there is additional science to show and prove that these are, in fact, hips and femurs and not just some random bone. We can see this in people. We have a tailbone. If you've ever fallen really hard on your butt, you know this. Like, it can get cracked and bent, and it's very painful. Well, why would we have a tailbone? Unless we once had a tail. And in fact, I think it's like 1 out of every 100,000 people are born with this tiny little nub tail sticking out, right around here, because instead of curling down, it curls out. It just happens. It's not even that unusual. So these are vestigial structures in people. And oh man, we have all kinds of vestigial structures, right? The goosebumps that we get is the same thing that a cat has. When the cat gets freaked out, its hair lifts up. It looks bigger and puffier. We think that's cute because we're bigger than a cat. If we were smaller than a cat and we saw that, it would probably look terrifying as this predator suddenly doubles in size. We have things like the appendix, which is a little tiny blob hanging off the large intestines that used to be used for something. Now, seemingly, its main goal is just to get infected and cause a life-threatening condition that we need surgery to fix. Wisdom teeth. Really important if you go back even a couple hundred years, because dental care didn't exist. We would lose teeth over the course of our life. They would rot and fall out. They would break and die, things like that. We needed a set of replacement teeth to come in around 20 to get us to 50. Well, we don't need them so much anymore, and you can see the evidence by how many people have their wisdom teeth removed, because when the wisdom teeth come in, that's the problem. Well, clearly then they're not needed anymore. They are vestigial. Great video about this. I will have it linked in Schoology, where they're dissecting a giraffe donated from a zoo. And there's this one nerve in the giraffe that is a phenomenal example of a vestigial or a leftover structure, something that wasn't planned, that doesn't work the way that it should. So these were Darwin's pillars. This was what he organized his theory based around, using the fossil record, the distribution, homologous, analogous, and vestigial structures. And with all of those, he was able to finally organize his theory of descent with modification, what today we call evolution, and make it public. And let people throw the proverbial stones, because his evidence was strong enough to withstand all of that. Now, this is also interesting to note. Do you remember last unit, Gregor Mendel, the monk in what is now the Czech Republic, who did all that genetics work with his pea plants? Well, Mendel lived in the same time period as Darwin. He wrote up all of his discoveries about inheritance. He sent a copy to Darwin. We know that. And if Darwin had read it, he would have had such an answer to some of the questions that Darwin still had, some of the things that he wished he could have had in his theory, because he could not explain them if he had read this paper. But evidence suggests that he did not. And so, unfortunately, it was missed. But that is going to bring us to modern evolution, where we take natural selection from Darwin, we take inheritance from Mendel, and by using those two together, we can really explain exactly how this works. All right, those individuals who are the most fit because they have inherited alleles that give them physical traits, a phenotype that is more successful. Because they're more successful, they survive long enough to have more offspring. And they pass to those offspring the same alleles, the same phenotypes that made them successful. If you do this again and again and again, the genetic differences are going to build up eventually to such a degree that the organism you have is no longer the organism that you started with. Case in point, your project last week. Ladies and gentlemen, I hope that this helps, that it clarifies some of these ideas that Darwin had. And going forward, we're going to be looking into how the modern side of science takes care of these answers and can continue to prove and support the theory. So, ladies and gentlemen, have a great day, and I look forward to seeing you in class.